Voyager 1 is running out of power. In April of this year, NASA reached across 25 billion kilometers of empty space and switched off one of the last instruments still working on humanity's most distant machine. The spacecraft is still alive. It is still transmitting. But it is quietly going blind, and the engineers running it are betting on a last resort maneuver they have nicknamed the Big Bang. What the probe detected in its final months of full operation is some of the strangest data ever returned from interstellar space. This is the story of what NASA actually detected before they shut down Voyager 1. On April 17, 2026, a command was sent from Earth that took nearly a full day to arrive. When it reached Voyager 1, the instrument known as the Low Energy Charged Particle Experiment, LECP for short, powered down. It had been running for 49 years. It had watched the solar wind rise and fall across the entire outer solar system. It had seen Jupiter's radiation belts, Saturn's magnetosphere, the collapse of solar particles at the edge of the heliosphere, and the strange, cold silence beyond it. And then it was gone. Two instruments now remain: a magnetometer, a plasma wave receiver. That is the entirety of Voyager 1's working science payload. Everything else has been turned off. The shutdown was not the end. It was a preparation for something else. NASA is running low on options, and the engineers who have spent their careers keeping these probes alive are about to attempt something they have never tried before. But to understand why the April shutdown matters, and why the Big Bang maneuver is the last real hope, you have to understand what Voyager 1 actually is and what it has been doing in a part of space nobody has ever been to. The spacecraft launched on September 5, 1977, from Launch Complex 41 at Cape Canaveral aboard a Titan IIIe rocket. That launch almost failed. The second stage of the rocket shut down early, leaving around 1,200 pounds of propellant unburned. The upper stage, the Centaur, noticed the deficit, recalculated in flight, and burned for far longer than planned to make up the difference. At cutoff, the Centaur had about 3.5 seconds of fuel remaining, 3.5 seconds between success and a dead probe in the Atlantic. If the same rocket failure had occurred on Voyager 2's launch just 2 weeks earlier, the Centaur would have run out of propellant before reaching the correct trajectory. Jupiter happened to be in a more favorable position during Voyager 1's launch window. The fuel margins worked out. The fuel margins on Voyager 2, with the same failure, would not have. That near miss is part of Voyager's origin story. The other part is that Voyager 1 was launched 16 days after its twin, Voyager 2, and still reached Jupiter and Saturn first because it took a shorter path. It has been ahead ever since. The spacecraft itself is built around a 10-sided bus, each side a compartment, a bay, housing different electronics. Bay 1 contains the radio transmitters, 16 hydrazine thrusters, 3-axis stabilization gyroscopes, a set of redundant systems for almost everything, designed to survive a mission that was supposed to last 4 years, not 49. At the center of the bus, pointing back at Earth, is a Cassegrain high-gain antenna 12 feet across. That antenna is still pointing at Earth today, pumping out a signal in the X-band at about 8.4 gigahertz, carrying science data at most a few kilobits per second. The mission was supposed to end at Saturn. That was the original contract. 2 gas giants, a handful of moons, a few good photographs, and then nothing. Voyager 1 made its closest approach to Jupiter on March 5, 1979, passing about 349,000 kilometers from the planet's center. During the 48 hours that bracketed closest approach, the probe took most of its best images of the Jovian moons, rings, and radiation belts. It watched Io erupt, active volcanoes on another body in the solar system, the first ever seen. Io turned out to be the main source of matter pervading the entire Jovian magnetosphere, sulfur, oxygen, and sodium. thrown up from the surface by volcanic eruptions and sputtered off by high-energy particle impacts, were detected at the outer edge of Jupiter's magnetic field. It found new rings around the planet, rings nobody had known were there. Then, it moved on. In November of 1980, it reached Saturn. It flew within about 6,400 kilometers of Titan, Saturn's largest moon, to study its atmosphere. Titan was the priority. The choice had been made long before launch. Voyager 1 could either visit Titan or continue on to Pluto. Titan won, because Titan had an atmosphere, and that was the only moon in the solar system known to have one. Voyager 1 measured the effect of Titan's atmosphere on sunlight, and Earth-based antennas measured the effect on the probe's radio signal as it passed behind the moon. The thick haze blocked any view of the surface, but from the composition, temperature, and pressure data, scientists speculated that lakes of liquid hydrocarbons might exist down there. They were right, though it would take another 30 years and another spacecraft to confirm it. That Titan flyby bent Voyager 1's trajectory down and out of the plane of the solar system. It would never visit another planet. The gas giants had thrown it upward and outward, and it was going to keep going in that direction until it stopped working. Voyager 2, with its different trajectory, went on to Uranus and Neptune. Voyager 1 just went. The thing is, nobody was entirely sure when it would stop working, and nobody was entirely sure what it would find along the way. This is the anchor. Voyager 1 became the longest experiment in space history, almost by accident. And LECP, the instrument just switched off, was one of the few things on board still listening when the spacecraft crossed into territory that had never been measured directly by anything ever built by humans. The first thing you need to know about LECP is that it was designed to measure particles, specifically how fast they were moving, what direction they came from, and how many of them there were. The easiest way to picture it is to imagine a piece of wood. The particles are the bullets. A fast bullet digs deep. A slow bullet barely scratches. By counting the holes and measuring their depth, you can work out what the particles are, where they came from, and how much energy they carry. That is essentially what LECP did for 49 years, across a distance no instrument had ever traveled before. Its principal investigator for most of that time was a scientist named Stamatios Krimigis at Johns Hopkins University Applied Physics Laboratory. He saw every particle LECP ever counted. The instrument itself is two solid-state detector systems mounted on a rotating platform. One detector, the low-energy particle telescope, points in whatever direction the platform has been rotated to face. The other, the low-energy magnetospheric particle analyzer, measures particles of a different energy range. Between them, they cover a span of energies that overlaps with the cosmic ray subsystem on one side and the now defunct plasma science detector on the other. Three instruments in a chain, each picking up where the last left off. Two of them are already dead. LECP was the middle one. And LECP, unlike the cosmic ray detector that was turned off in February of 2025, has been left with the option of reactivation. A small half-watt motor inside it is still running, just in case. The engineers are hoping to turn it back on. The reason they might want to turn it back on is because of what LECP recorded in late 2010. The outward flow of the solar wind had dropped to zero, not low, not weak, zero. Since June of that year, the detector had been returning a flat line. The solar wind, the constant stream of charged particles that the sun throws out in all directions, was no longer flowing past the spacecraft. Voyager 1 was, at that moment, about 116 astronomical units from the sun, or roughly 17 billion kilometers. The leading hypothesis was that the solar wind at that distance had been turned sideways, bent by the pressure of interstellar wind pushing against the outer edge of the heliosphere. To test this, NASA did something the spacecraft had not done in 20 years. In March of 2011, they commanded Voyager 1 to roll 70 degrees counterclockwise, to see if the solar wind had simply changed direction. The spacecraft rolled, reoriented itself using its guide star Alpha Centauri, and resumed transmitting. It was the first major maneuver Voyager 1 had performed since the family portrait photo in February 1990. That photo, the one that includes the image of Earth known as the pale blue dot, was taken from about 6 billion kilometers away. It is the last picture Voyager 1 ever took. After that, the cameras were shut down to save power. The imaging software was later removed from the spacecraft. The Earthside computers and software that could read those images are also no longer available. Voyager 1 could not take a photograph now, even if NASA wanted it to. It has forgotten how. The memory where that code used to live has been overwritten with other things. But it could still roll, and it could still measure particles. And in late 2011, it began measuring something very strange. On December 1, 2011, NASA announced that Voyager 1 had detected the first Lyman alpha radiation originating from the Milky Way galaxy itself. Lyman alpha radiation had been spotted from other galaxies before, but the Sun's own emissions had always drowned out the signal from our own galaxy. Voyager 1 had traveled far enough from the Sun that, for the first time, the Milky Way's Lyman alpha signature became visible. A few days later, on December 5, NASA announced something else. Voyager 1 had entered what they called a cosmic purgatory, a stagnation region. Inside this zone, the charged particles streaming out from the Sun slowed down and turned inward. The magnetic field of the solar system doubled in strength, as if something outside was pushing against it. Energetic particles born inside the solar system dropped by almost half. High-energy electrons coming from the outside rose by a factor of 100. Let that sit for a second. A factor of 100. Not double, not 10 times. 100. Something beyond the solar system had been there the whole time, and Voyager 1 was finally close enough to hear it. The inner edge of this stagnation region sat at about 113 astronomical units from the Sunday. Here's what was strange. The scientists expected that when the spacecraft finally crossed into interstellar space, the magnetic field would change direction. The Sun's magnetic field points one way. The galaxy's magnetic field points another way. A crossing should show up as a turn, but it didn't. The field had shifted only about 2 degrees. Ed Stone, the Voyager project scientist, described the situation by saying the mission had found a new region of the heliosphere that nobody had known existed. The magnetic field was now connected to the outside, he said, like a highway letting particles in and out. The field was 10 times more intense than anything the probe had encountered before the termination shock. But the direction was wrong, or the old model was wrong. For almost a year, the Voyager team could not tell which. The termination shock itself had been crossed years earlier. Scientists at Johns Hopkins initially believed Voyager 1 had entered it in February of 2003, but other researchers disputed the interpretation in the pages of the journal Nature that November. The argument could not be resolved at the time because Voyager 1's plasma detector, the instrument that would have measured the solar wind directly, had stopped working in 1980, 23 years before the event. The issue was eventually settled in May of 2005, when Ed Stone presented evidence at an American Geophysical Union meeting in New Orleans that the crossing had actually happened in late 2004. The estimated date is December 15, 2004, at a distance of 94 astronomical units from the Sunday. That's the point where the solar wind, racing outward at supersonic speeds, suddenly slams into the surrounding interstellar medium and slows down. LECP was one of the instruments that helped nail down the crossing in the absence of the plasma detector. The same problem came back with the heliopause years later. The plasma detector was still gone. Electron density had to be measured in a different way, through oscillations in the plasma waves, picked up by the plasma wave subsystem. triggered by a solar outburst that had happened a full year earlier and finally reached the spacecraft in April of 2013. When that data came in, it was conclusive. Between August 25, 2012 and the following spring, the electron density around Voyager 1 had increased by a factor of 80. Not small, not subtle. 80 times denser than the space it had just left. That's the fingerprint of the interstellar medium. Electron density outside the heliopause is expected to be 2 orders of magnitude higher than inside. The probe had crossed the final boundary of the Sun's influence on August 25, 2012, at about 121 astronomical units from the Sunday. It became the first human-made object ever to leave the heliosphere and enter the space between the stars. NASA did not officially confirm the crossing until September 12, 2013. By the time the announcement was made, Voyager 1 had already been inside interstellar space for more than a year. Additional confirmation came from the particle data. Starting in May of 2012, Voyager 1 had recorded a steady rise in collisions with high-energy particles above 70 million electron volts, which are thought to be cosmic rays coming from supernova explosions far beyond the solar system. By late August, the rise became a sharp jump. At the same time, collisions with low-energy particles, which are born inside the solar system, collapsed. Ed Roloff, the space scientist at Johns Hopkins who was principal investigator for LECP at the time, said that most scientists involved with the mission agreed those 2 criteria had been sufficiently satisfied. The only thing missing was the expected flip in the magnetic field, and the field had flipped by only 2 degrees. Some scientists suggested the old model of the heliopause was simply wrong. A new model was proposed. It predicted that no field reversal would occur at the crossing. That model fit the data. The old assumption was retired. Here's what's strange about this region. It isn't empty. For a long time, the assumption was that the space between stars would be mostly vacuum, with occasional thin clouds of gas and dust. What Voyager 1 has found is that the density of interstellar material near the solar system is higher than expected, and it keeps increasing the further the probe travels. In October of 2020, researchers reported a significant, unexpected rise in density in the space beyond the solar system, detected by both Voyager 1 and Voyager 2. The pattern seemed to be a large-scale feature pointing back toward the heliospheric nose, the front end of the Sun's magnetic bubble as it plows through the galaxy. Something about the interstellar medium near the Sun is piling up. Nobody is entirely sure why. In May of 2021, NASA reported the first continuous measurement of material density in interstellar space, along with the first detection of interstellar sounds. Those recordings are real. Voyager 1's plasma wave instrument picks up the vibrations of dense ionized gas, and when scientists play those vibrations through a speaker, they fall within the range of human hearing, a rising tone, a continuously increasing density, a sound the Sun has never made. To put this in context, here is the only comparison that really works. The closest probe to Voyager 1 in terms of capability and reach is Voyager 2. They are identical twins. Same design, same instruments, same mission. Voyager 2 left the heliosphere on November 5, 2018, about 6 years after its sibling, at a distance of 119 astronomical units. And when Voyager 2 made the crossing, it saw something Voyager 1 did not. Voyager 1 had discovered 2 interstellar flux tubes that had somehow invaded the heliosheath, essentially fingers of galactic magnetic field poking into the Sun's territory before the boundary itself. These were precursors, warnings. Voyager 2 crossed the same boundary and found none of them. Just a clean, sharp crossing, followed by a thin boundary layer where low-energy particles streamed outward along the magnetic field and cosmic rays were only about 90% as intense as they were further out. Same boundary. 2 completely different experiences. The edge of the solar system is apparently not symmetrical. And this is why shutting off instruments matters so much. Every time one goes dark, a particular way of understanding the outer heliosphere goes dark with it. The plasma detector on Voyager 1 died in 1980, which is why the termination shock and the heliopause crossings both had to be reconstructed through other means. The photopolarimeter had already been turned off in January of that same year because of degraded performance. The imaging science subsystem was shut down in February of 1990. The infrared interferometer, spectrometer, and radiometer was terminated in June of 1998. The planetary radio astronomy investigation went dark in January of 2008. The ultraviolet spectrometer was terminated in April of 2016. The cosmic ray subsystem was turned off on February 25, 2025. And on April 17, 2026, LECP joined them. All that remains on Voyager 1 are the magnetometer and the plasma wave subsystem. The first tells us about the strength and direction of magnetic fields. The second tells us about the vibrations of the plasma around the spacecraft. They are two very thin windows on a region nobody has ever explored. Now, let's come back to the shutdown and the maneuver that might, if it works, bring some of this lost capability back. The reason LECP was turned off is almost absurdly mundane. The spacecraft is running out of electricity. Voyager 1's 3 radioisotope thermoelectric generators, RTGs for short run, on the decay heat from plutonium-238 in the form of an oxide pressed into small ceramic spheres. Each RTG contains 24 of them. Alpha particles released by the radioactive decay hit the inside of the container, generating heat. That heat is converted into electricity by thermoelectric converters. It is not a complicated design. It is, in fact, one of the most reliable power sources ever built for a spacecraft. The problem is simply time. Plutonium-238 has a half-life of about 87.5 years. Voyager 1 has been flying for nearly 49. The fuel is more than halfway depleted, and the thermocouples that convert the heat into electricity have been quietly degrading the entire time. At launch, the RTGs produced about 470 watts. Today, after nearly half a century in flight, they produce about 225 watts, and they lose roughly 4 watts per year, every year, without pause. A heater turned on back in October of 2024 triggered the fault protection system and briefly knocked the X-band transmitter offline. The system lowered the transmission rate, and engineers managed to find the signal. Then, on October 19, the transmission stopped again. The fault protection system had switched to the S-band transmitter, a backup that had not been used since 1981. 43 years without activation. It worked. The X-band transmitter was reactivated later, and the team resumed collecting data in mid-November. But the incident was a warning. The margins are no longer margins, they are knife edges. In late February of 2026, a routine roll maneuver on the 27th caused an unexpected power drop that set the stage for the April shutdown. Power margins, according to JPL, are razor thin. The team is shutting off heaters, instruments, and subsystems, one at a time, while trying not to let the spacecraft get so cold that the hydrazine in its fuel lines freezes. And so the Big Bang. That is the actual internal nickname for what the engineers are planning. The idea is to swap out an entire group of powered devices at once, turning some off, replacing them with lower power alternatives rather than trimming one component at a time. The hope is that the net saving will be enough to bring LECP back online. That small half-watt motor inside LECP has been left running for exactly this reason. The first Big Bang tests will be conducted on Voyager 2 inches May and June of 2026 because Voyager 2 has slightly more power and is slightly closer to Earth, which makes it a safer first patient. If the procedure works, the riskier attempt on Voyager 1 is scheduled for no earlier than July. The phrase "no earlier than" is doing a lot of work there. There is no guarantee any of this will succeed. The reason timing is so tight has to do with a single antenna in Australia. Deep Space Station, 43 inches. Canberra is the only antenna on Earth capable of sending commands to Voyager 1 and Voyager 2. Between May of 2025 and February of 2026, that antenna was largely offline for major upgrades, with only limited operational windows in August and December of 2025. During that stretch, the engineers had to revive Voyager 1's backup roll thrusters before the full communications blackout hit. They succeeded. In May of 2025, thrusters that had been considered unusable since 2004 were brought back to life. Thrusters that had been shut down because of clogging problems in their hydrazine lines. A thruster swap in September of 2024 had already moved the spacecraft off its then primary set onto a less clogged set that had not been used since 2018. Voyager 1 is now, as project manager Suzanne Dodd of JPL put it to a reporter, entirely single string. There are no more backups. Everything on board is the last of its kind. The memory situation is no better. The spacecraft's total memory is 68 kilobytes, not megabytes, kilobytes. In November of 2023, the Flight Data Subsystem, one of the 3 onboard computers, began transmitting unreadable data to Earth. A repeating sequence of ones and zeros. A stuck signal. NASA announced in December that the telemetry modulation unit could not communicate properly with the FDS. A reboot of the computer did not help. For months, Voyager 1 kept sending a carrier tone, enough to confirm it was still alive, but no meaningful science or engineering data at all. Commands sent to alter the modulation of the tone succeeded, which meant the probe could still hear Earth. It just could not talk back properly. In April of 2024, engineers identified the problem. A single memory chip inside the FDS had been corrupted, probably from being struck by a high-energy cosmic ray particle or simply wearing out from age. 3% of the chip's memory was unusable. The code that needed to run lived in the broken section. The fix was to move the code somewhere else. But there was no somewhere else. The spacecraft has no spare memory. To create space for the relocated code, just 256 bits of it, the engineers had to delete old code that was no longer needed. One of the blocks of code they deleted contained the instructions for transmitting data from Jupiter. Voyager 1 no longer knows how to talk about Jupiter. It doesn't need to. The Jovian system is 47 years behind it. On April 20, 2024, communications of health and status were restored. On May 22, NASA announced that science data from 2 of the 4 instruments then active had resumed. On June 13, all 4 were returning data again. All the data from the anomaly period from November 2023 through April 2024 is lost. This is the spacecraft that is about to attempt the Big Bang. A machine running on a power budget measured in single watts. A computer with 68 kilobytes of memory, 3% of which has been ruled permanently dead. A single antenna in Australia that handles every command. 2 working instruments. Backup thrusters revived after 21 years of dormancy. Fuel lines that must be kept above freezing. Any signal sent to Voyager 1 now takes roughly 23 hours to reach it. Any reply takes 23 hours to come back. 1 full Earth day for a conversation. Not a round trip, a single reply. The spacecraft is projected to reach a distance of 1 light day from Earth in November of 2026. That is a milestone no object built by humans has ever reached. A full day of travel at the speed of light, just to check in. There is a lot we still don't know. We don't know whether the Big Bang maneuver will actually work on Voyager 1. We don't know why the density of the interstellar medium keeps rising as the probe travels further from the Sunday. We don't know why the magnetic field at the heliopause barely changed direction when Voyager 1 crossed it, or why Voyager 2 found a completely different boundary 6 years later at almost exactly the same distance. We don't know why Voyager 1 had interstellar flux tubes reaching back into the heliosheath, and Voyager 2 had nothing of the kind. We don't know what's in the gap between the heliopause and the Oort cloud because nothing has ever been there to look. Voyager 1 is expected to reach the theorized Oort cloud in about 300 years, and to take roughly 30,000 years to pass through it. No instrument on board will be awake when it gets there. The RTGs may continue producing enough power for basic engineering data until around 2036. After that, both probes will drift out of range of the deep space network entirely. In 40,000 years, Voyager 1 will pass within about 1.6 light-years of a star called Gliese 445 in the constellation Camelopardalis. In 300,000 years, it will pass within less than a light-year of another star with a catalogue name and no common one, somewhere past the orbit of Ophiuchus. A decagonal box with a 12-foot dish antenna is still pointed at Earth. It is moving at about 17 kilometers per second, roughly 3.5 astronomical units per year, carrying a gold-plated record with greetings in 55 languages, the sound of a baby crying, whales singing, waves on a shore, and music by Mozart, Blind Willie Johnson, Chuck Berry, and Valia Balkanska. It has 2 working instruments left. It is 25 billion kilometers away, and any signal it sends now takes almost a full Earth day to reach us. In a few months, a team at JPL will try to bring one of its dead senses back to life. It was never built to last this long. Nobody thought it would.